Today we'll be discussing neural networks. So neural networks have really taken the field of machine learning by storm, and in majority of the application areas now, they're considered to be the state of the art. But this was not the case a few years back. In today's lecture, we'll also do an overview of some of the history of neural networks and try and understand how we got where we have got. The the most noticing thing about neural networks is that they presented a very important paradigm change in the way we think about machine learning. So traditionally what we used to do was consider this image and say you want to classify this. This is a very classic MNIST like data set. Let's say you want to tell this digit from 1 through 9. What you would do is to create some features out of this image. What do you think those features could be? We might be looking at some horizontal edges, some vertical edges, the number of, let's say, circular patterns in this, maybe the intensity of the black versus the intensity of the white, or the number of filled pixels, so on and so forth. So we'd create features like intensity, horizontal line, vertical lines, percentage blank, etc. We'd, after curating all of these features, we would feed them to a classifier where we would eventually learn the importance of each of this feature and how each of this feature contributes to the overall prediction. Now this classifier could be as simple as a logistic regression here, which we have just discussed before we took the mid-semester break. So we call the features that we've created as handcrafted features, whereas the classifier is the trainable component of this whole pipeline, right? So just to summarize this, in this entire pipeline, we have a feature extractor component, which is effectively hand curating or crafting some features. This is not really trainable. Only the classifier component of this pipeline is trainable. In contrast, if we consider the neural networks or many of the more advanced or recent machine learning approaches, you'll see that you're just given the input and the output, and you're trying to create an end-to-end classifier. So there is no need to manually or handcraft some features. All you need to do is to create, let the machine itself figure out some of the low-level features. This could be edges, some high-level features compared to these edges. This could be, let's say, a combination of a vertical edge and a horizontal edge, and then build a classifier on top of that. So this is really helpful in the sense that you do not need to handcraft those features, which requires a lot of domain expertise and is fairly non-trivial to do in many cases. And neural networks have now been shown to outperform many of the existing methods. So the paradigm change here is that the features are curated in the pipeline itself, using the machine will learn itself how to curate those features, and more importantly, everything is in this pipeline is trainable. So even the features that you learn are learned to be the best possible features you could have got for this particular classification task. So this was a major change in neural networks compared to many of the existing methods. We'll now be talking about the perceptron, which was, let's say, one of the earlier methods, which eventually led to what we now know as neural networks. But before we do that, let's quickly watch a video to get some historical background.
Success of neural networks has sparked the AI revolution in the last 10 years, from Atari games to Go to Dota and to StarCraft. What many people don't know, the basic idea of neural networks has been around since the late 1950s. Welcome to the origins of neural networks. In 1957, Rosenblatt invented the perceptrons, a type of neural network where binary neural units are connected via adjustable weights. He was inspired by the work of neuroscience in the 1940s, which led him to create a crude replication of the neurons in the brain. He tried many different layouts and learning algorithms. Computers at the time would have been too slow to run the perceptron, so Rosenblatt built a special purpose machine with adjustable resistors controlled by little motors. This really is a physical machine. When the neural networks learned, hundreds of little motors went on and turned little knobs to make adjustments. The apparatus was able to classify different images of shapes or letters. The New York Times reported the following on the perceptron. The Navy revealed the embryo of an electronic computer that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned.
In 1969, the book Perceptrons was published. It was a harsh critique on Rosenblatt's perceptrons. It demonstrated that the perceptrons sometimes failed even on extremely simple tasks like the XOR problem. At this time, they already knew that using multiple layers would be able to fix this problem, but there was no algorithm to train such a network at this time. It took 17 years until such an algorithm, now known as backpropagation, was devised. Only later on was it discovered that the backpropagation algorithm had been discovered before. Indeed, it turned out that the backpropagation algorithm had been invented before the book was even published. So now, 17 years later, with the invention of the backpropagation algorithm, which allowed neural networks to theoretically approximate any function, surely a breakthrough was about to happen. But neural networks just didn't really took off in a big way. Why? Find out in The Rise of Neural Networks, to be released next Friday. Subscribe.
I hope you enjoyed that video. It showed a glimpse of a few years, a few decades of research in neural networks, and it was fascinating to see how the person who was operating that machine was manually toggling a switch to tell whether the prediction was correct or wrong. So imagine a human in the loop having to do that in those early years now. And for now, what you need to just do is to just provide a training set, which has an array which specifies the ground truth, and you just compare the prediction to the ground truth. It's fairly trivial now, but earlier someone had to manually toggle the switches. And you might also find interesting how the entire machine was a gigantic machine. It would probably be bigger than some of our classrooms also. And those who've anyway had a chance to see things like what broke the Enigma machine and so some of the work of Turing might see that these machines are similar in size. Now, the same neural network or the same task which those folks were doing then can probably be done in milliseconds in your smartwatch also. So this is just to show how much things have changed. But I think what was really important there to see was that the perceptron, they presented that perceptron model was initially adapted a lot, but then it faced a big hurdle in the sense that it could not solve problems like the XOR problem. In the next 10 or 15 minutes or so, we'll see what that exact XOR problem is. And this is where Geoffrey Hinton's work was really groundbreaking. Although, as the video says, that this had been backpropagation had been studied in different contexts, in different literature. But we'll see and we'll really appreciate that how this particular algorithm paved the way forward for neural networks. But before going to backpropagation, we should first understand the perceptron, what it can do well and what it cannot do well, and why we needed backpropagation. So the perceptron was a simple artificial neuron developed by Rosenblatt in the 1960s, and it was inspired by some earlier work by McCulloch and Pitts. The important thing to note here is that the perceptron only took binary inputs and only gave a binary output. And you could have as many binary inputs as you want. And this unit in between, or the computation unit in between, is called the perceptron. The key idea of the perceptron is that for corresponding to each input, in this case x1, x2, x3, we assign some weights w1, w2, w3, which are then aggregated in some sense, and some decision is taken based on this aggregation. So this is so the simple formula which the perceptron uses is to first do the summation of weights times the input, summation wi xi, and see if it is less than threshold or greater than threshold. And if it's this sum is lesser than the threshold, then the output is 0. If the sum is greater than the threshold, the output is 1. A fairly trivial algorithm, a fairly trivial way of predicting, which, so we have been seeing some fairly similar methods thus far. We can also write the same algorithm or the same perceptron in a slightly different fashion. Oh, by the way, this threshold is, this is how some people also thought that neural networks are connected to the brain, that the neurons will fire above a certain threshold. This is how some scientists have shown that the human brain also works, but I think the parallels don't go the complete way between the neural networks which we use in machine learning and the human brain. There is a limit to the parallels. And W's are the weights. We can instead introduce a bias term and add another feature which is a constant 1. Doing so, now instead of computing the threshold term, writing in terms of the threshold, we can simply write that the output y hat is 0 if summation wi xi plus b is less than 0, and it is 1 if summation wi xi plus b is greater than 0. So that's it to the entire model. It's a fairly trivial model. We'll be now looking at some examples and try to make the understanding a little more concrete. Just to summarize, the neuron that we see has two components, and we'll be looking at this kind of convention throughout this lecture. In pink, we see the first component, which is a summation component, which is summation wi xi plus b. And then there is an activation component. In this case, the activation is a step function. So if you see, we said that if it is less than or equal to 0, then the output is 0. And if it is greater than 0, then the output is 1. So there is an operation being operated on top of summation wi xi plus b. And in this case, it's a step function. And the step function in fact looks like this. So the step function will be, if z is greater than 0, then it is 1. If z is less than 0, it is 0. And at z equal to 0, you could arbitrarily define it to be, the output to be either 0 or 1. And if you see, this resembles the shape that we have drawn here. Okay, looks good. Let's try to now learn some binary gates using the perceptron model. You're given this data for a binary and two inputs x1 and x2, and so we already know this truth table was, if both x1 and x2 are 0, the y is 0. If only when both x1 and x2 are 1, that the y is 1. Your goal is to learn the wi's and b so that for this particular training data, we can learn a binary AND. Right? So I would urge you to think for a minute or two and tell the values of W1, W2, and B. Okay, I'm assuming you spent a minute, paused the video, and thought through this. The answer which I have over here is W1 is 1, W2 is 1, and B is minus 1.5. So one way to think about how to come up with these weights is to see that you want only when x1 and x2 are 1, you want the output to be 1. Or you want basically summation wi xi plus b to be greater than 0. So W1 is 1, and if we multiply that with 1, we get 1, plus W2 is 1, multiplied with x2 equal to 1, you get 2, minus 1.5, you get 0.5, which is greater than 0, so thus the output is, thus we get the last row. And for any of the other rows, if you see, so since 1 is less than 1.5, if you have only one input being 1, then you'll always get the output as negative, and thus the step function applied over that would be 0. So thus, using this particular set of weights, we can learn the binary AND using a simple perceptron. Let's take another minute and try and learn the Wi, Bi, and B for a binary OR. The truth table now is sort of flipped. Now it is 0, so the output is 0 only when both of the inputs are 0, otherwise it's a 1. I'm assuming you stopped the video and you thought about the solution. The solution which I have is W1 is 1, W2 is 1, and B is minus 0.5. By the way, you could have anything in proportion to these numbers also, and you could have various other possibilities which would still satisfy and give you the correct answer for a binary OR. This is just one simple way I thought about the solution. Let's just verify. If both the inputs are 0, so then summation wi xi is 0, and plus b is minus 0.5. Thus, overall summation wi xi plus b is negative. Thus, the output is 0. But even if any of the inputs between x1 and x2 is 1, then summation wi xi would be greater than or equal to 1, and you subtract 0.5, the output would be greater than 0, and apply the step function on top of that, you will get the predicted y hat as 1. Okay, now thus far we've been seeing two inputs. Now let's try learning a binary gate for a unary input, which is just try to learn the NOT gate. You have an input x1 and the output is y. Again, think for a minute and try to work it out on your own. Okay, I assume that you stopped the video and thought about the solution. This is again a fairly simple question, and we can choose W1 to be minus 1 and B to be 0.5. Thus, when x1 is 1, the summation wi xi plus b becomes minus 0.5. Thus, the output is 0. And when x1 is 0, so then the summation wi xi plus b is 0.5, and thus the predicted output is 1. Okay, let's now take a minute and think about learning a NAND gate. NAND gate, if you forgot about it, it's just the NOT of AND. Assuming you stopped and thought through this. One of the approaches to just directly learn some values, x1, x2, and b. And if you note these set of values, they might look fairly similar to the values which you saw for AND. Let's go back and see the values for AND. Right. So the values for AND for minus 1.5, 1, and 1. And the values that you see for NAND are 1.5, minus 1, and minus 1. So you see that the weights and bias have been negated. You could work it out and come up with the weights like this, or you could construct first the AND gate and then take a NOT of it. That's what the NAND gate effectively means, and you could just do it that way. It's left up to you that to figure out in the best way in which you can learn a particular gate. So I'll quickly walk over how the learning happens here. Thus far, we've seen that we sort of figured out on our own that what these weights could be. But in machine learning, we generally start with a random set of weights and bias, and we have to figure out that the optimum set of weights for this classification problem. So we're given an input x, which is n samples, d dimensions, and the ground truth y, which is n samples, one dimension. We have a learning rate, LR parameter, and we have LR hyperparameter and IT hyperparameter, which is the number of iterations. So as you would have figured out, this is fairly similar to gradient descent, given the set of parameters, and we need to, using something similar to gradient descent, figure out the optimum weights. The first thing which we do is just a convenience thing. Instead of writing as summation wi xi plus b, we just absorb and we just create another column in the input corresponding to the bias term, and corresponding to that we can create a weight w0. So you augment x to x prime such that the first column of x prime is all ones. We initialize the weights randomly. Now the weights, if you see, is a d plus 1 dimension, where the first dimension is the w0 term corresponding to the bias. And then, as you do in gradient descent, you repeat the iterative procedure over multiple iterations. And then what we have is that for each of the n examples, you walk through them and you update the weight. Right? So this is somewhat similar to stochastic gradient descent in that sense. The first thing we do is to predict what is our y hat. Again, fairly similar to what you would do in gradient descent. To predict what is y hat, you calculate the error, which is y minus y hat. So in gradient descent, instead of just calculating the error, you would also calculate the gradient in which, so the direction in which you want to update the weights. And in this case, you're just calculating the error. And finally, you update the weights as on a per sample basis. So W is updated as W plus learning rate into error for the nth sample into x prime of n. So only for that particular sample you update that. For each sample you update the set of weights. Error n is the error in the nth sample, and x prime of n is the nth sample. And as I was drawing out the relationship between gradient descent and this particular algorithm, so n and n is analogous to stochastic gradient descent. You are updating the weights per sample, and corresponding to the error term, which you multiply the learning rate with. Here we have the error in the nth sample, which is analogous to gradient and gradient descent. A quick intuition as to why this algorithm makes sense. Let's imagine that we have the set of weights as 1, 1, 1, and x dash n for the nth sample is 1, 0, 0. The first row will always be 1, if you remember, because this is the artificially introduced bias column corresponding to bias, right? And we know that the ground truth y is 0. So if we apply this w x, if we multiply w with x dash n transpose, what we'll get is, or w transpose into x dash n, we'll get 1 into 1 plus 1 into 0 plus 1 into 0, which is overall 1. And since it's greater than 0, the y hat prediction would be 1. But the ground truth prediction was 0, right? So which of these three weights do you think we should be changing amongst W0, W1, and W2? So you might have seen that W1 and W2 are as such not participating for this particular example because the input itself is 0. So it might already make sense to you that we need to somehow reduce the first weight or weight W0, right? Now let's look at the update rule, which is W is updated as W plus learning rate into error for the nth example times the nth example itself. Now we calculate the error for the nth example as y minus y hat, which is 0 minus 1, which is minus 1. We update W's as W, so W, which is 1 on 1, plus learning rate, let's say, is 0.01 into error for the nth example, which is minus 1, times x prime n, which is the nth example itself, which is 100. And if you update this, you'll get W as 0.9911. If you see W has now moved in the correct direction as you would have expected, although by a really small amount. So if over multiple iterations and multiple examples, you should eventually get there. So that's the idea behind the Perceptron learning algorithm. I'll now walk through a Jupyter notebook that I've written for Perceptron learning. As usual, I've imported the standard packages, NumPy, Matplotlib. I have created an X input array, which consists of x1, x2. This is just binary inputs that we're dealing with. And I've created 3 different Ys corresponding to AND, OR, and XOR. So AND of 0, 0 is 0, AND of 0, 1 is 0, AND of 1, 0 is 0, and AND of 1, 1 is 1. Similarly, I've created the AND, OR, and XOR. And this is the class I've created for Perceptron based on the formula or the algorithm that we just saw. The input parameters or input hyperparameters are the learning rate and the number of iterations. I have defined the activation, which I mentioned earlier, is just like is a step function. So whenever it is greater than 0, the output is 1, otherwise it's 0. And there are 2 methods now required. One is the fit, one is the predict. So thus we saw the algorithm for learning the parameters, which is equivalent to fit. If you remember, the first thing which we did was to create x prime, which is the first column of x as all ones. The second I've done is to initialize the weights. In this case, I've initialized the weights with all zeros. You could have just randomly done that. And then for each iteration, and then I loop over all of the examples. What I've first done is calculate summation wi xi, right? So that is just the dot product of the x prime with w, and I then can calculate a y hat or the prediction. So this prediction is based on the activation, whether it's greater than 0 or less than 0. Based on that, you assign either a 0 or a 1. Then you calculate the error term, which is y minus y hat. And then finally you have the update term, which is w equal to w plus learning rate into error for the jth example into the inputs. And then I've just done some reshaping operations, which you don't need to worry about. And the predict method is fairly simple. You again compute x prime, which is just appending the first column of x's of 1s to the first column. You compute the summation, which is summation wi xi, or just the dot product of x prime with w. And then the y hat is just the activation on top of the summation that you get. And then you can return that. I'll show the usage of this for some examples. I instantiated this class with the default parameters, which I believe were learning rate 0.01 and iterations equal to 100. And I fit x and yr. So I'm trying to now learn the parameters for the OR gate. And if you see the weights that I learn after this exercise are 0, 0.01, and 0.01. And if we go back and see the weights which we were using for binary OR, they were 1, 1, and minus 0.5, but again, it does not matter. You can I mean, you should be able to learn different equivalent set of parameters which still satisfy the problem at hand. For AND gate, we are able to learn minus 0.02, 0.02, and 0.01 as the set of parameters. And for XOR, we learn the parameters as 0.01, minus 0.01, and 0. And we predict for the XOR problem on X, and we get a wrong prediction, which might come to you as a surprise, might not come to you as a surprise, depending on how much you followed the kind of decision boundaries which the perceptron can learn. So the output should have been, let's go back, have been 0, 1, 1, 0. So what this is saying is that even on the train set, you have prediction of 50%. You're not able to learn the perceptron even on the train set. Forget about generalization, right? So before I go and show how we can still use the perceptron in the algorithmic procedure, let me show you how I would think about this from a visual perspective using TensorFlow Playground. And another utility of TensorFlow Playground is to also establish the fact that how neural networks can learn the features on their own without us having to handcraft them. Okay, so I'll just remove this. Right, I'll keep the activation to sigmoid. Right, so let me clean this up. So this is your original data set. This now looks like an XOR problem, right? For the specific XOR problem which we've been using with binary, we just have 4 inputs. But in this case, this has a similar structure to the XOR problem. What I've done is I'm using 2 features, x1 and x2, which is similar to what we've been seeing in the binary classes, except these are not binary, these can be real. And I've created one neuron. So this was just a summation wixi, and then the activation which I used here is the sigmoid instead of the step function. There are reasons why sigmoid is preferred over the step function, and we'll come to that. But for now, let's just see that this is sigmoid. By the way, this is, if you use a sigmoid with one neuron and whatever number of input features, this is effectively logistic regression. So let's try and run through this and see what we're able to learn. You can see the test loss and the training loss over here. The training loss is going down, the test loss is also going down. But as you could see, we are not doing a very good job. I can remove the discrete output and show you we are not doing a very good job in terms of prediction. We are able to just classify whatever, we are misclassifying these set of examples. And that's primarily because in this kind of a setup where you are using just a single neuron and a single layer, and basically logistic regression, you're learning a linear classification boundary, which cannot classify this data set properly, right? So what can we do? So one way to still just use logistic regression framework is to add more complicated features. And this is how, as I was mentioning at the start of this lecture, a lot of machine learning was done. There was a lot of handcrafted features. So why not? Let's add some handcrafted features. Let's add x1 squared, x2 squared, and let's try and see if we get something better. So as soon as we add x1 squared, x2 squared, you see that we can please now get nonlinear boundaries, but this doesn't seem to be sufficient. Now we are still missing out on this particular circle. If we got 2 circles, that would have been perfect, but we don't get that. Let's add another feature, x1, x2, and restart the process. And now you see that this particular feature seems to be really doing well. And in fact, if you look at the weights, most of the weights are close to 0, and it's only the weight of x1, x2 term which seems to be significant. Just to make things even simpler for us, we could do, let's say, L1 regularization. restart this. That would just drive the weights to be perfectly 0 and not just close to 0. So if we look at the weight of x1, x2, x1 square, x2 squared, they're all zeros. What this means is that the only feature which is important here is x1, x2. So this is the perfect example of how, if we are able to handcraft some features, we can learn arbitrarily complex decision boundaries, but this handcrafting is non-trivial. In this case, you saw that x1 squared and x2 squared, you might have thought would have been useful, but that didn't happen. So instead, let's now revisit the whole motivation behind neural networks, one of the main motivations behind neural networks, and see that we are not going to use all of these complicated features. Let's say we only have 2 features. I'll be doing something like adding multiple neurons and adding multiple layers. Don't worry if you don't get this right away. We'll keep repeating this entire process and we'll see a formal method. We'll introduce some convention and then introduce this concept. Now with this kind of a network, let's try and see what we're able to learn. I should first remove any regularization, and just to speed things up, I'll be using a different activation. Let's run this and see. Now at this point, it seems that we are sort of stuck, and we're not doing any better than what a simple linear logistic or simple logistic regression would have done. Let's try to give this a little more time and see if we're able to learn. So you see that till this point the learning was almost stopped, and then suddenly we started moving in the right direction. And now if you see, we're able to learn a fairly complicated shape. In fact, not a very complicated shape in this case, but we have not introduced or handcrafted any complicated features. The neural network is able to learn all of these on its own, and this is where it derives a lot of its strength. Let's try and see a more complicated example. And because it's complicated, I'll add, let's say, a few more layers, etc. Again, the input space is fairly trivial in this case. It's just x1 and x2. Some of the features it's able to create on its own might be able to, let's say, learn this. And let's see what we get. Again, it seems that we've sort of hit a point where we are not improving significantly. Let's give it a little more time and you'll see that suddenly things start changing. So now you can appreciate that this network is able to get this part of the classification correct. And you can see that the training loss is still going down, which means that there is still improvement in this. In fact, what is happening is that the model is now getting more and more samples correctly, maybe 1 at a time, 2 at a time, and thus the training loss is going down. Now, in order to get this particular structure correct, this particular part of the spiral correct, it has wrongly sort of started classifying these points. But since the training loss is going down, I'm still hopeful that it would be able to rectify this particular thing. And if you see now, gradually the model decides that it's better to not label all of these points as blue. It has got some part of the spiral already, and the training loss is still going down. Okay, so in the interest of time, I'll stop here. But this is a very fun exercise to do to try and understand what is happening. And let me just pause this. And you can, in fact, also see the weights and the individual features and what these things are learning. Let me remove the discretization. So if you notice that this is learning a very simple feature, that everything in the top half is a blue, one class, and everything below is 0. Now this is a feature which is just going diagonally. So again, if you look at the first layer, a linear feature, a linear feature, a linear feature, and a linear feature. you have 4 linear features. Now the second layer, you see that some of these first level features or low level features have now been combined. So if we look at this particular first feature or first neuron in the second layer, it is mostly getting weights from the first feature and then some weight from the fourth from the sorry the second particular feature of the first layer, and that is why it is assuming this structure. And if you see, and then if you finally go down to the next layer, now you can see more complicated features being learned. And if you were to add more and more layers, we can get now more complicated decision surfaces. So this is effectively the strength of neural networks. Okay, we'll now just try to graphically again understand why a perceptron model was not able to learn the XOR gate. As you would have guessed by now, and by looking at the previous video on TensorFlow Playground, the previous demonstration on TensorFlow Playground, XOR is a non-linear decision surface, decision boundary. And perceptron, thus far, we've seen that it can only handle linear perception, linear decision boundary. So if you look in the case of and I'm using red to indicate 0 class and green to indicate class 1, and we can see that so one of the boundaries which can be represented here is x1 plus x2 equal to 1.5. Anything above that is 1, anything below that is red or 0 class. Similarly, for OR we can create a decision boundary. In this case it's x1 plus x2 equal to 0.5. But for XOR we cannot create a single decision boundary because it's not linearly separable. And what we require is a decision surface something like this. And as we saw in the TensorFlow Playground example, we could do this by adding more layers to the network, and we can let the network itself curate some more complicated features, or we could ourselves create more complicated features and feed to the perceptron. So even the perceptron should be able to then learn such decision surfaces. And so one such feature that I've created here is x1, x2. So based on x1, x2, some values of x1, x2, and 1, as I showed earlier, we can perfectly classify this. So some of the weights, some of the combination of weight that you can learn here is the bias is minus 0.5 and the weights are 1, 1, and minus 2. But we've seen earlier that you can have x1, x2 is probably the only important feature here. So in this particular set of slides, I was just walking through this particular example, and for the 4 cases of XOR, if x1 is 0, x2 is 0, x1 0, x2 0, let's run through this. So 0 into 1 plus 0 into 1 minus 0.5. Since minus 0.5 is less than 0 and x1, x2 is also 0. So minus 0.5 less than equal to 0, the output prediction is 0. But if we take the second example, x1 equal to 0 and x2 equal to 1. So in that case, minus 0.5 plus 1 and plus 0. Since this is greater than 0, we predict this to be 1, which is green class. Oh, sorry, this should have been greater than equal to 0. And this should also have been greater than equal to 0. I'll hopefully rectify this. And for the fourth example, if both of x1 and x2 are 1, so 1 into 1 plus 1 into 1 minus 2, since x1, x2 is also 1, so then this entire thing is 0, minus 0.5 is 0. Thus, this is the red class. Or we could have also defined in terms of x1, x2 bar. And if you've done digital logic, then this particular representation of features that I've shown would make a lot of sense to you. So this is just to summarize what we have discussed thus far. Neural networks presented a paradigm change going from networks or pipelines where there was handcrafted features and then there was a trainable component to going to end-to-end learning, including learning the features. And to make this entire pipeline useful, we have to introduce some amount of non-linearity. So if you didn't introduce the non-linearity, you can, if you keep on building features on top of features, there'll just be some linear combinations. So this is left as an exercise to try and see if you create features on top of features or linear functions of linear functions of linear functions. Will you get something non-linear or something non-trivial? You will not be able to get that. You'll only be able to create another linear function. So that's why it's important to introduce some amount of non-linearity amongst these trainable features. Now, let's go back and watch another video. So thus far we have seen that we have seen that perceptrons are limited. They cannot learn anything with non-linear decision boundaries. You can of course hand curate features, but we've also seen that we can create, as you saw in the TensorFlow playground, we can create multiple layers, and then you can create these hierarchy of feature representation and learn something fairly complicated. But this is where neural networks got stuck for a lot of years until Jeff Hinton and group were able to discover or to implement the back propagation algorithm, which meant that now neural networks with multiple layers could be learned, because otherwise perceptron was able to learn only for a single layer or fairly trivial such networks. So that particular algorithm which Hinton and group used was called backpropagation, and the idea for backpropagation is to make things backpropagate. You require to compute some gradients, which requires, and wherever you want to compute gradients, you require smooth functions or continuously differentiable functions. But thus far, we had been seeing that in a neuron for perceptron neuron model, we had a summation term and we had a step function. And as we've seen in the case of logistic regression, we want to replace the step function with something which is smooth and differentiable at all points. So in logistic regression, we use the sigmoid activation, and for any neural network in general, you could use sigmoid or similar such activation functions. So the key idea remains use something similar to step function, but have it differentiable. Otherwise, backpropagation or gradient-based learning will not happen. Before I go into the details of backpropagation, let's watch the other video and try and understand the historical importance of backpropagation.
In 1986, the world of neural networks was about to change. After decades of silence, finally, a method to efficiently compute the weights in a multi-layer neural network was invented. The stage was set for a revolution. Welcome to the rise of neural networks. Now, with the invention of the backpropagation algorithm, which allowed neural networks to theoretically approximate any function, surely a breakthrough was about to happen. The AI researchers were excited and started working on neural networks again. This time it will work and no problem will be left unsolved with the magic of these networks. But as time went on, most researchers slowly drifted away from using neural networks and went on to try different methods, like support vector machines or Bayesian-style methods, as neural networks just simply didn't deliver like expected. Many even discarded the idea of machines learning in general, and went on to focus on handcrafted algorithms to infuse machines with intelligence. Still, some researchers worked on neural networks and were able to build cutting-edge systems like this one.
By the way, those who have still not recognize this person. This is Jan LeCun from, I think, late 80s or early 90s, where he was working on systems to automatically detect or write handwritten, recognizing handwritten checks. And just imagine how difficult it could have been to do all of this computation and probably writing neural network code in C or C++ at that time.
which could classify handwritten digits. The speed of the system was impressive at the time. It even went on to have commercial success, reading nearly 20% of all bank checks written in the US in the early 2000s. But this kind of work mostly happened in the dark. Nowadays, AI researchers open source most of the work and knowledge is easily shared. But this was not a thing back then. Around the year 2012, the world of machine learning was flipped on its head. Several breakthroughs in many different fields were achieved around this time. The yearly occurring ImageNet competition, for example, was won by a neural network for the first time and by a wide margin. The researchers were shook as they had discarded the idea of neural networks for a long time. Similarly impressive results were achieved in many different domains, like speech recognition or game playing. This sparked a revolution, and machine learning using multi-layer neural networks was at the forefront of this new period of AI. The amount of data created every day by the internet, smartphones, and other devices enables neural networks to flourish. For reference, in 2002, the amount of data created per year was estimated to be about 5 exabytes, while the data created per year in 2019 is estimated to be 10 zettabytes. This is an increase with a factor of 2,000. At the same time, GPUs or graphic cards which can process data in parallel were becoming widely available, and techniques to train on them effectively were being developed. Together, the increased computing capabilities and data access have reached a critical mass and allowed deep neural networks to outperform classical approaches in many different fields. This is why neural networks have risen to the state they are in now. We should be on the lookout. Maybe techniques we have discarded in the past will make a comeback, just like neural networks did. There are still many mysteries left to solve. Only the future will tell.
I hope you enjoyed the video and got a fair idea of how the field has progressed in the previous few years and how this was largely infused by the backpropagation algorithm, which was largely a factor of choosing the activation functions and then deriving gradients or the learning based on them. So the idea of supporting backpropagation and also learning complex feature representation is centered around this idea of adding nonlinearity via nonlinear transformations, which are differentiable. So instead of the step function in the second part of the neuron, we now write a general function which is g of z, and the first part of the neuron, which is the summation, is z now, which is summation wixi plus b, and we call this the output of the second part of the neuron as a activation, which is g of z, a nonlinear transformation. Various such activation functions have been studied, including sigmoid function, which we saw in logistic regression, whose functional form is g of z as 1 over 1 plus e to the power minus z. And we've already discussed this, that if we have one neuron and g of z equal to 1 over 1 plus e to the power minus z, we get logistic regression. So logistic regression is one of the simplest kinds of neural networks that you can learn. And then there are several other activation functions, like the hyperbolic tan or the tan-h, which is fairly similar to sigmoid, but it's between -1 and 1. And the functional form of this is g of z equal to e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. Then there is the game changer or rectified linear unit, which was also used in the 2012 paper by Jeff Hinton and group, and since then has become more or less the de facto activation function in neural networks. A very simple activation function which just says that g of z is z if z is greater than or equal to 0 or 0 otherwise. Or you can alternatively write this as g of z is the max of between 0 and z. There's another variation of ReLU or rectified linear unit called leaky ReLU, which is max of alpha z and z, where alpha is some greater than 0. The idea is that in ReLU there is, so g of z is 0, constant for z less than 0, but in leaky ReLU you have g of z as still a factor of z, but it's a small factor, so typically alpha would be less than 1 definitely. So which means that if you were to differentiate g of z with respect to z for ReLU, you will, so basically you're differentiating a constant when z is less than or equal to 0, but in leaky ReLU you are not differentiating a constant. You'll still get some gradient and you'll still get some learning. A quick summary of these activation functions. The sigmoid is generally very useful for probabilistic estimates when you're trying to predict something between 0 and 1, which is what we were exactly doing in logistic regression. We were trying to predict the probability of a particular class, and that was between 0 and 1. Tan H is very useful if the data is transformed with mean 0 and it is residing in minus 1 to 1. ReLU, as I discussed a minute back, was the game changer, generally the default activation function mostly. And leaky ReLU is fairly similar to ReLU, but it can do some learning. Learning means gradient computation even when z is less than 0. So I'll do one final slide before we take a break, and we then discuss some convention associated with neural networks, and then we'll look at the back propagation algorithm itself with some examples. So the activation functions, as we've discussed, have two main desirable properties. One is they have a non-linear transformation like effect, which allows us to build complicated features and not just linear transformations. And secondly, what you want is that a small change in the input leads to a small change in the output, which also is, you would have seen, as related to the property of continuity and differentiability. Okay, so with this, I'll stop the current discussion. In the next discussion, I'll talk about multi-layer perceptron and the corresponding convention and how we move from left to right computing in a network, and how we move from right to left, or we propagate backwards to learn the parameters. Thank you.